So limits, not too bad. Got all the homework done? Yes, Miss Calvert. Every single question is completed. All right. So we are going to start derivatives today. We're going to keep it pretty basic. We're going to go over 2 of them today. Okay. So we're going to use our prior knowledge to see if you guys can make a connection if we sketch one of them. Okay. So this one, using the graph of f of x equals sine x. Do you guys agree that that is the sine x graph? Right? So using our knowledge on how to sketch a derivative graph, let's remind you guys, remember how we start these little guys if I want to sketch the derivative graph? Right, the zero. So we go to all the max and mins. Do you guys agree? Because remember, the derivative graph is the slope of this graph, right? So we go to all the max and mins, and we know that at all the max and mins, the slope is 0. So all of these little guys right here, we can plot a point at 0. So just use your eyeballs about where that max ends. So I know the slope at that max is 0. So I'd plot a little point. And then at the next min, at that point, the slope is 0. And then at the next max, the slope is 0. And then at the next min, the slope is 0. So we do that first. That's the easiest, quickest starting of sketching a derivative graph. So then the next thing is on either side of those intercepts, we just look to see if the slope is positive or negative. So on this side of, not that you have to draw that dotted line, I'm just giving you guys quadrants to look at, so when I reference it, you guys know what I'm talking about. Okay, so don't do these dotted lines. Right, but that's kind of what you're visualizing. So on the far left here, the slope is what? The graph. This piece of the graph is a positive slope. Do you guys agree? So that just means on the left-hand side of that point, the line or the graph is going to be above, right? The x-axis. From that x-intercept to the next one, what's the slope there? Negative. So that just means that the graph is going to be below the x-axis from those 2 intercept points. So watch. So I know that it's going to be above first because it's a positive slope. It's going to keep the same shape. And then do you guys agree that it's going to be below between the next 2? So below. So it's got to come back up. And then it's going to be what? Above. Does it make sense, guys? It has to have the same height. It can't go past the height of the original. Right? So it's going to be above, and then at that next x-intercept, it's going to start going where? So it was above between the middle 2, and then the next 2 is going to go below. Bless you. And then after the last x-intercept, it's going to go, bless you, above. I don't like how it looks there. Anyway, pretty good. Do you guys recognize that graph? It's a cosine graph. So guess what? The derivative of sine is cos. Cool, hey? So we sketched it, but I'll still show you the proof, okay? But again, your derivatives are on your formula sheets, but it's super nice for sine and cos. The derivatives for sine and cos are super quick and easy. So again, as soon as you guys see a sine, right, and I'm asking you to find the derivative of the sine, you know automatically that it's cos. It's obviously going to get a little bit more complicated than that. It's not always just going to be find the derivative of sine. It might be find the derivative of sine squared 2x minus 4 close brackets, right, plus blah, 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 right? So with the sketch, it looks like, right, that the derivative of the sine graph is the cos graph, okay? Now, down below is the actual partial proof using formula 2 from chapter 1, okay? You don't have to do the proof. I just want to show you the algebraic proof. It's almost finished. We're going to have to finish the last 2 lines together. I'm still going to go through the proof to make sure you understand it, but you never have to prove it, okay? All right, so do you guys, I put these 2 pictures here. They're not in your notes, but do you guys agree that we've already went through those 2 limits? Right, so I just put them there to finish the proof with you guys. All right, so everybody recognize it? Right, so this proof is using this limit to prove, okay, that the derivative of sine is cos. All right, so I'm going to make it big so you guys can see it. All right, so if f of x is sine of x, okay, using this formula, does the first step make sense? Does that one make sense? Right, we just substituted it in. Now the next step, does that one make sense? Right, so some of you are like, huh? So remember, do you guys remember your sum identity? So that's what that is. So if you didn't remember your sum identity, that second step would have been like, where did that come from? So this right here, sorry, I'll unhighlight so you guys can see. Right? So this right here and this right here is just using the sum identity off your formula sheet, because we know that the sum identity for sine is sine x cos y plus cos y sine x. Do you guys remember that? So that's what they're just using here. They're using an x and an h instead, but it's just using the pattern off the formula sheet. Everything else stayed the same, so they just did that substitution in the proof. Okay. And then what did they do in the next step? Did they do anything crazy in the next step? No, they just moved stuff around, right? All they did was just they flipped the last 2 terms just to put terms together so we could factor sine x out. Right? So this step didn't do any substitutions. They just moved these terms, the order of those 2 terms is all they did. Right, and then this step, do you guys clearly see what they did? All right, so they just factored out a sine x. And then from there, they just separated the 2 of them, right? So no actual math, they just separated it into 2 separate limits. Do you remember doing that? Can we do that on each term? Right? Technically, you didn't have to write that. It's just nice to see it separate. And then, right, they just factored the sine x out of the limit just because the limit is in terms of h. Do you guys agree? So anything that doesn't have a in terms of h scenario, right, can be brought in front of the limit. Just like we did last class, any numbers, right, we brought outside. Here, the limit is in terms of h, so the sine x can come out, right, because we're not putting anything into that piece, right? We're only putting the 0 into the what? The h. Okay. So then from there, right, and then same thing on the second limit, right? We brought the cos x out just because it doesn't have an h. We're not applying the 0 to it. So we're just took it outside in front. So now, let's finish what we know. So this little box right here, what can we replace that with? 0. And that's from prior knowledge, right? So that's why I reminded you, you guys don't have these little graphs, but from last class, right, we learned I haven't done the proof on it yet. I'm still going to do the proof of y, right? But right now we just have the visual that this scenario, okay, does end up being 0. And is it backwards to what we have? But a negative 0 is still a 0. Right? So then this whole piece we can change to a 0 plus cos x times 1. Right? So sine x or sine h over h. Right? If we approach it to 0, we learned last class that that equals 1. So that would be the proof, right? You don't have to do the proof. You just have to use now that if I'm asking you to find the derivative, right, of sine x, you can replace it with a cos x. Simple as that, okay? So the only two we're doing today is the derivative of sine and the derivative of cos, okay? So are we all very comfortable that the derivative of sine x is cos x? So we're going to use that knowledge now to find the derivative of cos x, right? So flip to your next page. All right, so we're going to find the derivative of cos x. So we'll use a correlated identity to rewrite f of x equals cos x in terms of sine, since we know the derivative of sine x is cos x, okay? Because that's all the knowledge we have right now with derivatives of trig functions. All right. So scan all those correlated angle identities and find one in terms of sine, because there's a couple that you could pick, right, that is the same as cos x. Which one do you guys want to use? Because do you guys see what I'm talking about, right? Do you guys see how this one equals cos x? This one equals cos x. Is there any other ones that equal? So negative cos x doesn't work because it's not the same. So we have two options. Okay. Which one do you want to use? Because it doesn't matter. First or second? Second? Is that what I heard? And again, doesn't matter. We'll get the same answer. All right. So if we use the second, right, you're saying cos x, or we're saying cos x is the same as sine pi over 2 plus x. So we're trying to find the derivative of that. Okay. Now we're going to go back and put our derivatives brains on, and we have to now be okay with, right, our product rule, our quotient rule, our sum and difference, and then chain rule. Okay. So with something like this, do we have something on the inside? So we are going to have to use the chain rule on this. Okay. So how this works doing the derivative is do the outside. So what's the derivative of sine? So cos, inside function, stays, not function, it's the angle expression now, I should say. It's not a function anymore like chapter 2 was. So the expression for the angle stays, and then now the derivative of the inside would be just, what's the derivative of pi over 2 plus x? 1, okay. Pi over 2 is just a number, guys, right? Right, so the derivative of a constant is 0, and then derivative of x is just 1. All right, so we could say the derivative of cos x is cos bracket pi over 2 plus x, but look above. What else could we say it is? Do you guys all see that it's negative sine x? All right, so we're just looking right here. Right, so we're just looking here. So it's just nicer to say, instead of every time you see cos x and writing, oh, it's the derivative of it is cos pi over 2 plus x. Yeah, not nice. Nicer is negative sine x. Oh, goodness. Come on, don't freeze up. There we go. So negative sine x. So those are the only two we're going to work with today. Okay, we'll do some of the other ones next class. So all we're working with today is the derivative of cos x is negative sine x, and the derivative of sine x is cos x. Again, on your formula sheets, those are the only two we're going to play with today. So, how does that look? All right, so find dy dx in each of the following. So we're going back to chapter 2, all of our rules. So this little guy here, again, the angle position, right? If there's something in there, you're doing chain rule. Okay? So you start on the outside and work your way in. So if I want to do the derivative of y equals sine 4x, right? Y prime equals, what's the derivative of sine? Cos. And remember, the inside function stays. Right? And then what is the derivative of the, and I keep saying function, the expression for the angle, it's not a function really. I guess it's still a function. 4x is a linear term. What's the derivative of the inside? 4. That's it. Right. Obviously, they'll get more complicated. Can I go 4x times 4? No, because you guys know it's like wall of China. Nothing can get in the angle position. Right? So it's 4 cos 4x. Right? That is solid concrete. Nothing can get in there. Right? Because it's describing what's happening to the angle. Okay? Times in the whole thing by 4 does not affect the angle. Right? That is more what you would know as like a vertical stretch. All right. So this little guy here, okay, anytime you have like a sine squared or sine cubed or cos cubed, rewrite it, because this looks confusing right now how this is going to work. So I always rewrite these, right? Because this technically, do you guys agree that it's sine x squared plus 3 times sine, x cubed bracket x squared plus 1 means it's timesing sine x squared plus 1 3 times, right? Do you guys agree that that's what that means? I'm not going to write it 3 times, but what I am going to write it is in a way that you guys can visualize this better, because then you will clearly see what's inside and what's outside. Is that technically the same thing? Right? Everybody okay with that? So I got to go straight off with the chain rule, right? Because you guys know as soon as you see an exponent, right, are we chain ruling it? Yes. So this here would be, so deal with the 3 first. So then it would be 3 sine, everything inside stays, sine bracket x squared plus 1. And this is all squared. And again, you could put the square here or you could put the square there. I'm going to actually do it the way students prefer me to do it. They like it better. Do you guys agree? Now do I got to keep moving in? So then now the next piece is the sine, right? So what is the derivative of sine? Cos. So the next piece is cos. Does the expression in the angle stay? Yep, so cos squared plus 1. So that's my next piece. And then now I do the angle position. So then the angle position is 2x. Now this usually students are like, oh, it's wasn't so bad. Okay. This is the piece, though, that you have to make sure your formula sheet is there, because a lot of times, especially when you're using the chain rule like this, please keep an eye out for anything that looks like something like this, because this identity, do you guys agree that we've used this identity a lot? See if you can find that pattern, because if you can find that pattern, you're expected to simplify it. Or I would expect you to simplify it. So can we make that pattern out of this mess? Because remember, does the x have to be an x? Right. Find that pattern. This can be something else. right? It can be a 10x. It could be a x plus 1, as long as in the angle position they're equivalent, the same, right? Try to find that pattern. So I can definitely find that pattern in here, right? So watch what I mean. I'm going to rewrite it so you guys can see it. So y1 equals 2 sine x squared plus 1 cos x squared plus 1 times 3x sine x squared plus 1. I want you guys to see what I did. Because it's all products, can I move stuff wherever I want to move them? Right? So does everybody see what I did? Because I did have 2 sine x squared plus 1s, right? To make that pattern work, I had to break one off, right? So that's all I did, is I broke one of the sine x squared plus 1s off, right, to create the pattern, right? So do you guys see that pattern now? So then this whole thing, right, so this whole thing now I can replace with, exactly, right? So this whole piece, so remember, in the pattern it's an x. I'm changing it to a x squared plus 1, right? So that means right here in the pattern, guess what you put in for that x? In for that x becomes a x squared plus 1. So as Kaya says, when you write it down, right, you're going to get a sine. So we have to times that by 2. So sine 2x squared plus 2. And then we have a 3x sine x squared plus 1. I can't leave it like that, but this would be okay. Guess what I have to do, because it'll bother me. What do I have to move? Nothing's bothering you. You guys should know me by now. Yeah, the 3x can't stay there. Even though if you wrote it like that on your quiz, would you be good? Yep, I just can't. I just can't. Because again, I know products, it doesn't matter, but leaving a monomial in the middle like that looks, even though they're all, it just looks funny. So you could totally stay at the second step there, above from the bottom. But so it's not that, I would say this is the main pattern, okay, that students forget about. But it's the double identity patterns that will pop up. So just always have your formula sheet out, and just when you feel like you're done a question, like so something like this, just go, does that look like any kind of pattern I can create? Not from, like when you guys are looking at your formula sheet, not all the crazy co-identities. Those ones, I'm talking about the ones you're used to from 30-1, right? So your Pythagorean theorem identities and your double angle identities. Those are the only ones, your patterns you're looking for, right? None of the other ones they're not going to come up. Okay. All right. So this little guy here, hoping it's jumping out at you. What operation's happening there? Multiplication, right? So if there's a product to start off with, you have to use your product rule, right? You can't just take the derivative of x cubed and then times it by the derivative of cos x, right? We've never done that, right? We can't do that. It's not equivalent. We proved in chapter 2 you can't just do that. So that's why you have your rules. And again, on your formula sheet, right? So we know that it's f times g prime plus g times f prime. Do you guys agree? Right, so that's our derivative pattern. And we know that with products, does it matter which one you do first, which one you do second? No. But with quotient, it does. Okay. Remember, with quotient, the bottom has to come up, and then you take the derivative of the top. That order does matter. Here, it doesn't matter. All right, so which one do you guys want to do first? Derivative of x cubed or derivative of cos? X cubed. So if we do the derivative of x cubed first, then it's going to be a 3x squared times cos x. And remember, it doesn't matter if the derivative comes first or not the derivative, right? So I wrote the derivative second, but again, this is the same thing. Doesn't matter because it's equivalent. Right, and then plus, so then derivative of cos is negative sine x times x cubed. Right, so 3x squared cos x minus x cubed sine x. And technically, this pattern, right, not on our formula sheet. Sometimes, like if it was on an answer key, I would give full marks for that, but on an answer key, it would probably do this. But I wouldn't take marks off if you didn't do this, if it's on your quiz. But you guys know that with your assignments that I give you, and I give you an answer key on your assignment, do I expect you to get to my answer? Yes, that's the expectation, right? But when it's a quiz, we talk about where's good enough, right? So to me, doing this step didn't help you go further, right? It's not negative exponents, things like that. So either one would be good. Right. So feeling not too bad, guys? Right? So yeah, like I said, chapter 2, right? If you're solid in chapter 2, you're just redoing chapter 2 with 2 new derivatives, right? That's it. Right, so bless you. With this one, guess what I'm doing first? I am going to, right, well, I will do the squared, yes. I'm just going to rewrite it because anytime students try to deal with this, they go right to doing sine first, right? Can we deal with the sine first? No, it's a degree 2. So I find students that just quickly rewrite this, never do the order wrong, right? Because we know that sine squared just means the entire thing is being squared. When it's written like that, then you see the chain rule kind of hit you in the face, right? So we have to deal with the degree first. So away we go. So then the 2 comes down. So we have 2 sine x to the power 4. And then that's all going to be to the exponent of 1. So do I have to write the 1? Do I have to write that? No, I'm gonna, since I did it and I don't want to erase it now. All right, so then now next, so working our way in. So now we deal with the sine. All right, so now we're dealing with this piece, right? Because we're always going back to the original when we're working our way in. So then derivative of sine is cos, right? And then it's a x to the power of 4. And I don't have to put square brackets. Could you guys just keep writing right side by side? I'm just chunking it so you guys clearly see each piece, right? Just because it's been a little while, okay? So then I'm done with the sine. So now I got to do the inside piece. So the inside piece is just going to be a 4x cubed. Now that we talked about it, do you guys see the pattern very quickly? Right? And that's usually what happens. Normally, why would you ever look for that? Right? But now that I've told you, look for it, it's going to pop right out at you. Okay? So this right here, I don't even need to move anything. Is this the pattern right there? Right? Oops. Okay, stop doing that. There we go. Ah. Okay. Right, so that's the pattern right there. So I can replace that whole thing. So y prime equals, so this is going to be sine what? Right, 2x to the 4. So remember, all you do, guys, is replace whatever's in the angle position, that gets put by the 2, right? Or gets multiplied by the 2, because it's 2x in the original, right? So that is now replaced with the x. So then it's 2 times whatever that is. So then it's just 2x to the 4. And then we have a 4x cubed still left over. So I'm going to put that at the, I want to put it at the beginning. So 4x cubed. And that's nicely simplified. All right, almost done. So here, what are we doing here? Implicit differentiation. Because see how this one's not rearranged for y? So can we, no, you're good, honey. Can we rearrange it for y? No. So since we can't rearrange it for y, not a big deal. We've done lots of these, so just start deriving. So derivative of cos is negative sine, what? Negative sine y. Now the derivative of the inside, so derivative of y is dy dx or y prime, whatever you've been using. So that side's done. Okay. Equals, so the derivative of sine is cos, inside stays. Now the derivative of the inside is 2. Okay. So can I now just divide the minus sine y off? Yep, and then you're done. Because remember, with your implicit differentiation, your goal is to get dy dx or y prime, whatever you're using, by itself. So this is actually, I would say, easier than the last two we just did. Okay. So then divide minus sine y, minus sine y. So then dy dx equals 2 cos 2x over sine y, and I'll put the negative on the top because I don't like leaving the negative on the bottom. And again, it doesn't matter, you can. Easy peasy. So your implicit differentiation questions, guys, when they show up in the trig, are going to be pretty basic. Can I move on to the next one? Okay. Almost done. Got to see what the hockey game's doing. Ah! Maybe, of course. Now it's going to freeze. Okay, good. All right. Yes, exactly. They don't want me to see the game. All right. So, with this one, this is going to look messy, but I promise you it's not going to be bad. So, do we have a trig function within a trig function? Yeah, but you still just work your way, because we can't get y by itself, so we do have to use implicit differentiation. So away we go. So derivative of cos is negative sine, but guess what has to stay beside it? Sine x. Right, so we're done. Now we do the inside. So derivative of sine x is cos x. And the derivative of x is just a 1, so I don't have to write the 1. Equals, derivative of sine is cos, inside function stays. Now derivative of the inside, so derivative of cos y is negative sine y, but derivative of y now is dy dx. Right, because over here, when I did the other side, when I did the derivative of x is just 1 because we're deriving it in terms of x. Right, so when we're deriving it in terms of x, when you have to derive a y, that's your y prime or dy dx. So then that just big mess gets divided off. Right, so then if we divide that off, right, so this whole thing, so we're dividing off a negative cos y sine y. So negative cos y sine y. And there's nothing you can do with that. The only thing you can do is get rid of the negatives. That's it. Right? So then your final answer would be sine x cos x over cos y sine y equals dy dx. So it looks scarier than it actually is, right? Because we're not used to leaving kind of such, well, actually that's not true. We leave messes all the time, right? Look, that looks like messes. So do be prepared. You will have implicit differentiation within the trig as well. But you just follow the process that you're used to. All right, last question. It only makes sense that we finish with find the equation of the tangent. It's been a while, okay? So find the equation of the tangent line, 2y equals 2 plus cos x at the point where x equals 5 pi over 6. So do we need to find the derivative, right? Because the derivative will get us our slope of our equation we're trying to build, okay? So y prime equals, derivative of 2 is 0, derivative of cos is negative sine. Right, so then that is my slope equation. So now I can find my slope by substituting my x in. So my slope is going to be negative sine. X gets replaced with 5 pi over 6. So then from here, we know that our over 6's are what reference angle? The 30. So 1, 2, 3 is cos. Sine is half, right? So I know that sine is half, but is it a positive half or is it a negative half? So 5 pi over 6 is what quadrant? 2, right? And if you don't remember, I just go 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, right? I just count by 6's. Or could you just type it into your calculator to see if it's a positive or negative ratio? Yes. So this is quadrant 2. So therefore it is a positive half. So I don't need so much space there. Right, so it is a positive half. Right, but is that positive half being times by a negative? Yes. So therefore my slope is negative 1 over 2. This is where you're going to maybe be like, the next step is going to be a little gross. In the sense of, normally at this step, do you guys agree that we take our ordered pair, we put it in for x and y, put our slope in for m, and we solve for b? Yeah. Normally our ordered pairs are kind of nice. Our ordered pair here is not going to be very nice, okay? Because it's trig. So let's get our ordered pair, because are we missing y? Yeah, so you have to find y. So remember, anytime you're finding a point, it's always on the original function you're using. So we do need to find y. So I'll just do it over here. All right, so y equals, so 2 plus cos, and we do need to leave exact. You can't just type it into your calculator. Unless you fluked out and you typed it in and it was another half, then yay. But it's not going to be, okay? So you do have to use your knowledge of your unit circle. So again, we already said that over 6 is your 30. So what's cosine at 30? 1, 2, 3. So it's root 3 over 2. But we already said that this was quadrant 2. You guys agree? So in quadrant 2, cosine is negative. So that is your ordered pair. Do you guys want to put it together right now, or do you want to leave it separate? You can leave it separate if you want. We can deal with it later. But you guys pick. Leave it together or separate. You guys pick. I don't care. Together? Okay. So I should actually say, do you guys understand what I mean? Separate or together? Get a common denominator or don't. Right? So if you want to put them together, then it would be y equals 4 minus root 3 all over 2. Do you guys agree? All right. So then your ordered pair is 5 pi over 6, comma, 4 minus root 3 over 2. So that is what we're substituting in for x and y. So y equals, let's go down a little bit, bless you. So y equals mx plus b. So y is 4 minus root 3 all over 2 equals m, which is negative half, times x, which is 5 pi over 6 plus b. So then I have 4 minus root 3 all over 2 equals negative 5 pi over 12 plus b. Talk to me if I say something that you don't like. So do I got to take the other piece over? Yeah. So then I have 4 minus root 3 all over 2 plus 5 pi over 12 equals not plus, equals b. So technically, could you say y equals negative 1/2 x plus 4 minus root 3 over 2 plus 5 pi over 12? Could you technically say that would be the equation? Yeah, you could. I'm going to do general form just because a lot of times they'll ask you to put a general form. It's tough for me to leave it that way. I would at least get a common denominator for all of them, but you don't have to. Okay, technically this is correct. I'm going to write general form though, because do you guys agree that general form will clean this up? Yes, general form will for sure clean this up a little bit. So if I do general form, right, what would I multiply everything by? I'd have to multiply everything by 12, right? And then I would take everything to one side. So I'm going to multiply by 12. Are you guys okay that I do it in one step? So I'm going to multiply everything by 12, but also move it over. So I'm going to take it to everything to the side where the x term is going to be positive. So I'm going to get a 12y, right? So if I bring the half term over, 12 divided by 2 is 6. It's a negative on this side, so it'll become a positive on the other side. So it's a 6x, right? And then here, 12 divided by 2 is 6. 6 times 4 is 24. And I bring it over, so it's a minus 24. I also have to times the root 3. Okay? So then that's going to be a plus 6 root 3. And then lastly, minus 5 pi. So remember, guys, since we put it together, right, when you guys divide the 12, that 6 has to get multiplied by both, not just the front one. And then all my signs changed because I brought it over. So when you're writing tangents with trig, general form, even though that's not super nice, but it's, I find, nicer, right, than the y equals mx plus b form. But like I said, you can leave it in the y equals mx plus b form if it doesn't tell you general. So looks funky, but same process that we're used to. Okay. So that is that. So these are some good startup questions for you guys to try. And then next class, we'll do some more derivatives of like tan and secant and stuff like that.